Welcome back. In this short segment, we're going to look at a few examples of sequences. First, let's build the first few terms of a geometric progression with a equals 2 and r equals 3. Remember, a is the initial term of the sequence, therefore a sub 0 is equal to 2. Then every term after that is obtained by multiplying the previous term by r. So 2 times 3 is 6, that's a sub 1. 3 times 6 is 18, that's a sub 2. 3 times 18 is 54, that's a sub 3, and so on and so forth. For our second example, we're going to look at an arithmetic progression with a equals to minus 3 and d equals to minus 2. Remember that the initial term is a, so in this example, a sub 0 is minus 3, and then every term after that is obtained by adding the common difference, d, to the previous term. So a sub 1 is minus 3 plus minus 2, which is minus 5. A sub 2 is minus 5 plus minus 2, which is minus 7. Minus 7 plus minus 2 is minus 9, that's a sub 3, and so on and so forth. Now for the next example, we're going to proceed the other way around. I'm going to give you the first 7 elements of a sequence, 7 real numbers, and I'm going to ask you to determine, based on these numbers only, if the beginning of this sequence follows an arithmetic progression, a geometric progression, or neither one of them. Now notice we can't tell from the first 7 numbers what the whole series or sequence is doing. So we're just going to base our decision on these first 7 elements or 7 terms. So how do we determine if these numbers follow an arithmetic progression? Well, we just need to check if the difference between any 2 consecutive terms is the same. So let's take an easy one. Let's say 6 minus 12 is going to be 18. So the difference from here to here is 18. Now the difference between minus 3 and 6, so minus 3 minus 6 is minus 9. So here the difference from here to here is minus 9. We already found a counterexample, so this is not an arithmetic progression, since if it were, the difference would be common. Remember, d is a common difference between all the pairs. So now let's turn our attention to the possibility of a geometric progression. Now the way this works, again, is you divide one term by the preceding one. So for example, if you divide minus 3 by 6, you get minus 1/2. If you divide 6 by minus 12, you also get minus 1/2. So now it's possible we could have a geometric progression here. So now we have to check them all to see if it works. So I'm going to go the other way around from one term to the other by multiplying by the common ratio. So 96 divided by 2 is 48. Put a minus in front, and that works. 48 divided by 2, that's the same as multiplying by 1/2, which is the absolute value of the common ratio we are hypothesizing. So 48 divided by 2 is 24. Change the sign because we're really multiplying by minus 1/2, 24. 24 divided by 2 is 12. We change the sign, we get minus 12. We already checked this one. We already checked this one. Now 3 divided by 2 is 1.5. And changing the sign is okay. So it looks like, at least based on this first 7 terms, this is a geometric progression where the first term is 96, that's the a part, and the common ratio is minus 1/2. Now for our last set of examples, we're going to define a concept that is a special case of a sequence, and that's called a string. Now in computer science, a string is a finite sequence of characters. The length of the sequence or string is n, and typically instead of writing the terms in a sequence separated by commas like here, we just write them down next to each other and put them between quotes, say. So again, a string is a sequence There are two specific properties of strings. One is that the codomain has to be a set of characters. Now, it doesn't have to be necessarily the letters A, B, C. It could be any set of characters, or more generally, symbols. Now, the second property of a string is that the sequence must be finite. At least in computer science, we don't have any infinite data structures, or in particular, we don't have any infinite strings. So a string is always finite, and it's a sequence of characters. Remember, in a sequence, there is an order, because the domain is a set of consecutive integers. So you can index the elements or the terms of the sequence, meaning the elements in a string, by their index. So here is an example. Or first, let's not forget the empty string, which is a special case, is denoted by either an empty pair of double quotes or single quotes, depending on the language. And in theoretical computer science, the empty string is usually called lambda. This is lowercase lambda, this is uppercase lambda, the Greek letter, or sometimes it's also called epsilon, another Greek letter. So these are the different possible notations for the empty string, which is the empty sequence. So, for example, the string hello is basically the sequence of 5 characters, HELLO, indexed from A sub 0 to A sub 4. Notice these are finite sequences now, they don't go on forever. Now, a second example is a bit sequence. In other words, it's a string of bits, or a bit string, where the symbols are just limited to the characters 0 and 1. So here is a bit string. These are obviously very useful as well in computer science, computer engineering, and so on and so forth. Another kind of string or sequence is the integer sequence, which of course in programming we call an integer array, or sometimes a list. So an array or a list is also a finite sequence, which is indexed by an integer, usually starting at 0. So for example, this one-dimensional array, in a pretty common notation with square brackets in many programming languages, is also a sequence of integers where a sub 0 is 10, a sub 1 is minus 5, and so on and so forth. Again, this sequence is finite, since we usually don't handle infinite data structures. So this concludes this short segment with a few examples of sequences.